Before we sketch the waveforms, I want you to give your attention to the range of the omega t value. The first and the second ranges are referring to the positive and negative half cycles of the AC voltage respectively. Usually when I sketch the waveforms, I prefer to use the VI characteristics of an ideal diode during forward bias and reverse bias as my reference. During on state, the diode should conduct current with zero voltage drop. Meanwhile, during off state, the diode must stop current conduction by blocking reverse voltage. Based on these characteristics, I will rearrange all the voltage and current equations. I will start with the current equations, the diode voltage equations, and lastly, the output voltage equations. Next, we use the equations to identify the shape of both voltage and current waveforms. According to the current equation in 2a, we can see that the current wave shape is similar to the supply voltage waveform. However, based on Vs divided to R, we know that the amplitude of the current waveform is lower than the amplitude of the supply voltage. On the other hand, based on equation 1a and 3b, we can see that the output and diode voltage waveforms have the same shape and amplitude as the supply voltage waveform. As a summary, the wave shape of the current, output voltage, and diode voltage is following the supply voltage waveform. Now, we need to sketch three sets of axes. The top axis is focusing on the voltage and current waveforms at the supply or AC side. Meanwhile, the middle axis is concentrating on the voltage and current waveforms at the output or the DC side. Lastly, the bottom axis is focusing on the voltage and current waveforms of the diode. Since all parameters are related to the supply voltage, hence we start the sketch by drawing the supply voltage waveform using its general equation. Based on the equation, the shape of the AC supply is a sinusoidal wave shape with an amplitude of Vm. Thus, according to the previous discussion, we now know that the current, output voltage, and diode voltage in these equations are also sinusoidal. For the next step, we need to sketch two vertical lines to separate the positive and negative half cycles of the supply voltage waveform. As discussed before, only during the positive half cycle of the supply voltage, diode D is in forward bias. Thus, we can use an arrow to label the range of the forward bias on the graph. So, we will know that the diode will conduct current only in this range. This range, which is in between 0 to pi, is known as the conduction range of the diode. From the range, we can calculate the conduction angle of the diode by subtracting pi with 0. As a result, the conduction angle of diode D is pi or 180-degree conduction angle. This conduction angle indicates that the diode is only conducting current for 180 degrees or half of a complete cycle of the rectifier operation. Lastly, we will sketch the remaining waveforms using these equations. As discussed, we will start with the current waveform. Since the current equations shown in 2a and 2b are referring to the output current, hence, we will sketch the waveform on the middle axis. Next, on the bottom axis, we sketch the diode voltage waveform. Finally, on the middle axis again, we sketch the output voltage waveform. To complete the current waveform of the AC source and the diode, we need to refer to the single-phase half-wave rectifier circuit. Based on the circuit, we can see that there is only one current pathway existed. Because of that, this output current is also the supply current and the diode current. By referring to the diode current, we can verify that diode D only conducts current for half cycle or 180 degrees only. Based on the complete waveforms, we can see that diode D can conduct current with zero voltage drop during the positive half cycle of the supply voltage. Furthermore, since current can flow to the load, thus we also have the output voltage waveform. In opposite, during the negative half cycle of the supply voltage, diode D will stop the current conduction by blocking a large reverse voltage. Since there is no current flowing to the load, therefore output voltage equal to 0. Lastly, the peak amplitude of the diode voltage waveform, which is negative Vm, is known as the peak inverse voltage or PIV. It's referring to the maximum reverse voltage a diode can block during reverse bias. Next, when we compare the voltage waveforms on the top and middle axis, we can see that the voltage waveform on the top axis is AC voltage, while in the middle axis, it is DC voltage. Hence, these waveforms have verified that the rectifier has converted the AC voltage to DC voltage. However, when we look at the current waveforms on both axes, we can see that both currents are DC. Based on that, we can state that the operation of the single-phase uncontrolled half-wave rectifier with a resistive load has caused the AC source to supply DC current. Therefore, this rectifier is not suitable to be applied in a real application.